The first baby example is the bordel conjecture. So we take C a curve over a number field of genus at least 2.
Could you make it a little larger?
Yeah, I try. Then the number of points of C is finite. So this was settled about 3 days ago. And the second is Manin-Mumford. Okay, so you again take a curve of genus at least 2. You embed the curve in Jacobian in some standard way, and you look at C and you cut it by the torsion points. And the claim is again that's fine. So this was settled also 3 decades ago. And in fact, it's pretty straightforward to see that these two cases are special cases of the so-called Mordell-Longue statement. So if you want to unify this, you come to Mordell-Longue. So what is the statement? So now you take V, you take it, you assume that it's sitting in the semi-abelian variety. Is it large enough, or should I make a even bigger? Okay. Okay. So now I take a semi-abelian variety. I fix a sub-variety sitting inside it, and then I take gamma inside A of K bar of finite rank. Okay. So this means that gamma tends to Z has a dimension over Q which is finite. Okay. And you look at V intersected by gamma. So if gamma is just the set of torsion points of A, okay, so this is case 1. And if gamma is just the Mordell-Weil group of the Jacobian, then this is case, first case was case 2. The Mordell-Weil case is just the Mordell conjecture. So you expect that this set is a bit special. And in fact, the statement is that it's a finite union of xi plus bi, where bi is a sub algebraic group with xi plus bi included in V. Okay. So this again was settled by following the work of Voita, Faltings, Macmillan. It was settled in the current situation more than 2 decades back. So end of the story? No. We have to maybe go back to the very easy case where since we have semi-abelian varieties, we can think just of the multiplicative groups.
You write the intercept gamma equal to this union. Do you mean included in this union? Or?
Is sorry. So I take just a curve C. I assume that it's sitting in Gm to the n. And I look what it means to have a torsion point sitting there. Just this situation. So if X is a point C in Gmn torsion, what does it mean? First, you have each coordinate taken to some power which is equal to 1. Okay, for some n. then you have f of x which is equal to 0 for all f in the ideal of definition of some. Okay? So this is plenty of equations. You think that the system is overdetermined. Okay? Just one equation like that would already bring you in dimension 0. So you expect that maybe you are asking a bit too much. And this is where you come to the statement of type Zilber thing, conjectures. Okay, so if you want to state them in full generality, it takes some time, because just to define properly the object would take about the lecture and the time I've given. So I just try to simplify and remain for the time being in the same setup with the semi-abelian variety and not go to the mixed case. So in that case, what I define is AR. So I want to reduce the number of equations. So I want to cut down this. So I will define AR to be the union of B, a codimension of B, at least R, and B a subalgebraic group. Okay? It need not be connected. There are a lot of torsion components. Okay? And so basically, in this case, I could afford to take just one equation. Now, if you have a curve, if you look at A1, it's already codimension 1, you expect codimension 0. But still there is a catch. This n you have varies, so you have uncountable countable number of possibilities. So it's a bit too much. And the question, on the other hand, would be to take, say, R at least 2. And maybe it's enough. So because you expect that if you have two equations, then it might be empty. Okay? So as Marsa puts it, sometimes he says that if you take an infinite union of finite sets, it's usually infinite. But if you take an infinite union of empty sets, maybe it's finite. And so this is basically what you expect. So the conjecture would state something like that. So you assume that V is not contained in any translate of a subalgebraic. Okay. You take gamma as a group of A of k bar of finite rank. And what about the base field? Well, for the base field, basically, as you can see, these conditions are pretty geometric. So you don't actually need to be over a number field. So basically, you can assume that K is any field of characteristic 0 for the time being. Finite characteristic might be a bit tricky, but you might be of and in any case, it will reduce by specialization argument to number field case. So it's, the proofs will be number theoretic. Then V of k intersected by gamma plus a dimension of V plus 1 is not Zaristian. Okay, so this is it. So indeed, if you just take two conditions like that, it should be enough to have finite. Okay, so now, and the special case of the Manin-Mumford conjecture or the Bordelon conjecture would be to go all the way to dimension 0. Okay. So this is the situation. What is the general strategy to prove such a statement? Strategy. First, you try to prove that the height is bounded. Say on B intersected by gamma plus A dimension of B plus 1. You have a set of bounded height. And then you try to identify properly exceptional locus. So you try to understand where the points of this intersection are going to accumulate. Okay. So in the model long case, it was very clear. It was subgroups which were sitting inside the variety. So in that situation, it might be a bit more complicated, but still you should have some kind of decent exceptional locus. So you need to understand that and show that it is a strict heuristic close. Okay. And 3, apply some lemma type bond. So what today I want to discuss is to discuss about the small points for step 3 of this strategy in relative situations. We shall go into semi-abelian cases to see what are the obstructions to move a little bit further. So exceptional locus, let us say a few words of this kind of thing. What should be the exceptional locus? So this now is pretty well understood in this situation.
So this A is the semi-abelian in which
Yeah.
B is there, is it?
Yeah.
A is the same hypothesis. B
Yeah,
is
same hypothesis. You are in the same situation and you try to understand how you would like to prove that statement. Okay. So now, where should the points accumulate? It's not too difficult to see that you have an obvious obstruction. If you have a point that's going to accumulate, then this kind of intersection has to be of large dimension. Okay. So you look at the set of X in B, and you look at the local dimension, the dimension at X of the intersection V intersected by X plus B for some translate of a subalgebraic group. So you take a subalgebraic group, B is always a subalgebraic group, you cut it like that, and so what is your expectation? Well, basically, if it was in general situation, the dimension of the intersection will be the codimension, the usual formula. Okay, so you ask whether it's bigger than the usual formula. So that usual formula is max of 0, dimension of B, plus dimension of B minus dimension of A, something like that. And you say, okay. So it's not completely clear that this set is a heuristic closed set. In fact, it was proven by Bombéry, Marsan-Zanier in the toric situation, by Gaël Raymond for abelian varieties, and by Jonathan Kirby in the semi-abelian case, using some modern theoretic arguments. So to understand step 1, maybe I'll just show you quickly the example of the curves sitting in the multiplicative group. So you look at a curve C and you intersect it by A1. A1 is A is just Gm to the n in this case. T is a curve. So this was proven by Bombieri, Marzani about 20 years back. Then the height is bounded. The height of x in C by A1 is bounded. So if you cut the curve x by just one equation, you get finitely many points. But of course, since you have countably many subgroups, you still have an infinite set. So it's a non-trivial statement to say that the height is bounded. Okay, and this is proven using variants of Néron's equivalence theorem. So it's not too difficult and not too surprising that the height is bounded. So this is more or less Néron's equivalence theorem. So in the case of curves, the exception set is not too difficult to understand, so you can forget about that. And you need to see what happens to lemma bounds. So I do it for Gm to the n, and then we shall extend the definition. So you take alpha in A to be Gm to the n in this case. I take B to be the smallest torsion subvariety, which means in this case just unions of translate of subtorus by torsion points, which is assumed to be irreducible over Q. Containing alpha. So this you call it P of alpha. And then you define omega of alpha to be the infimum for all z defined over Q, containing alpha and contained in B. Strictly contained in B. And you take the following ratio, dimension of Z divided by degree of Z divided by degree of B, whole to the power 1 over codimension of Z in B. And then the lemma conjecture, this is a variant of lemma conjecture, would be that there exists a positive constant depending only on T of A, such that if alpha is in A minus the torsion set, then the height of alpha is bigger than T of A by omega of alpha. So this is a classical way of looking at lemma conjecture now. Once you have this statement, you just assume this statement for the time being, and you see what happens. If alpha belongs to C intersected by A1, then you show that omega of alpha goes like the power of the degree of B. So this omega of alpha, which is a degree which should be large, in fact is very small. In the other hand, if you look at the height tends to infinity polynomially in the degree of the subgroup in which it lies. Okay. whereas you usually think that the height might go to 0 if you take division point. It cannot happen. And once you have that, you have here the height that goes to infinity with the degree, and on the other hand, you have bounded height. Okay? In other words, the possible subgroups in which alpha can lie have bounded degrees, and they are finitely many. And this is how you show finite many. So this is your strategy.
Is there an analog of Dobre-Walke's theorem that
Yeah,
you can use?
Yeah, and what you can actually do is to prove this to the power 1 plus epsilon. So this is known. This is basically a generalization of a result that I proved with Amoroso about 20 years back. And the full conjecture, and of course this is more than enough to prove the implication. So you actually can go through in the theory cases. So now I would like to see what happens in semi-abelian cases, because there you have interesting phenomena that happen and show that you need to be more careful. So I would like to point out that there is a construction of Bertrand, Daniel Bertrand, which is the following. You take a curve x, okay, and you have a b. These fibers G are extensions, semi-abelian varieties, which are extensions of elliptic curves by Gm. Okay, so it's a variety of dimension 3 with relative dimension 2. In such a situation, so Bertrand was able to make a construction of this kind, showing that there exists a section S of x to b, such that the image of S of x meets infinitely many times the torsion law. Okay. In other words, the naive generalization of Manin-Mumford cannot hold. You have to be a bit careful when you are looking at families. And this happens in fact, what it does is to use a construction like Jacquinot and Ribet, which was further generalized by Ribet, of points in semi-abelian varieties which has Bn strangely. So there exist points in such a G. G is simply an extension of an elliptic curve by Gn, provided that it's not isogenous to a pure product. Such a construction can be made. There exist points which have two strange properties. Firstly, if you take L to be the field, the base field generated by all the torsion points. So it's a huge field. And then P is infinitely divisible over N. In other words, you can perform Kummer theory without having to extend the base field. You can divide infinitely many times. Right? The linear part of the canonical height is equal to 0. So to define the linear form of the canonical height, I would need 4 minutes. So let us just assume that, in fact, you can define an extension of the Nérontate height over G such that m of p is equal to m squared times the Nérontate height of the projection, pi of p, plus m times a linear form. So basically what you do is to take the pullback of the variable line bundle 3 times 0 here, and you take the push out of O of 1 here, and you construct the height as Serre did a couple of decades ago. So if you take any of these two properties, you also see easily that a statement like lemma, like I stated, cannot hold. It is bound to be false. Because you cannot have a lower bound for something which is of height 0, and you cannot have a fixed lower bound of the height if you can divide infinitely many times. Okay? So the conjecture that I did want to suggest is the following. So let us be a bit. So I need a few notations. Let us make them. So the first thing that I need to know is that if I look at an abelian variety and I look at the possible extensions by GM, this is isomorphic to the dual. Okay? So in the elliptic case, you can identify the dual to A, and you can attach to such an extension of E by GM a point Q in the elliptic. So G, you can attach it to Q. Is the identification, and you can call your extension GQ. Okay? And you can do it, of course, for any extension by an abelian variety by a torus attached to a point in the dual. Okay? So let us, since the time is running short, let us just take the statement for extensions by elliptical. You just assume, so there exists a positive constant C of T, Q, positive, such that the following is true. If P is in G of K bar minus torsion, and the height of P is less than what you expect, which is some constant divided by omega of P, as defined above. Okay? Then you need to have an exceptional situation. Then something happens. Then you look at the projection of P. Yeah. So you have a decent point in the elliptical. You have this point parameterizing the elliptical, phi of Q, and these are dependent over the endomorphism ring. In other words, if labor problems fail, then your point has to be very special. It has to lie on a phi block such that the point P itself is linked to it. And in fact, it can be shown that these points constructed by Ribet lie on these things. So basically, the Ribet points are the points that are natural obstructions to lemma conjecture. So in fact, if you want the third step, the small I point, even in the non-relative situation, without basing, you do have obstruction, and you have to look for them. And if you try to generalize, this is the statement that I would like to propose. And what do I have to support that? You can do the same statement for any semi-abelian variety. And the result that you can prove is the following. theorem for every positive epsilon, if E is Cm, then the height of P, C of P, divided by omega of P to the power 1 plus epsilon implies P and Q. Okay. In other words, you have the Dobovorsky kind of statement, provided you are outside this exceptional case. And in most general situations, I can do it if the abelian base is Cm elliptic, or if the abelian base is of small dimension, less than 3, and the fiber, the toric part is of dimension 1. Okay, and I still do have some issues in proving the general situations where you have any abelian variety, Cm abelian variety, and any multiplicative group. And just maybe one sentence about the idea of the proof. If you are in the Cm case, you follow the idea of the Dobovorsky that the Frobenius map lifts to an anamorphism. So you have an elliptic curve, you have a place V, you have the Frobenius V, which is an anamorphism. You have Fv here. 0, 0. You have your projection phi. You have your group G. You have your Gn. Here you have multiplication by P. That's the decent lift of Frobenius. And then you would like to come back to G. So unfortunately, this is not true. You have to go to G of Fv of P. So in fact, when you have such a map, you can complete the group, but you are outside of the group. You fall into a new group. So that doesn't matter. What you actually do is to perform all your Diophantine geometry on E1 on this fiber plane, which is basically the Poincaré B extension. So you perform your Diophantine construction on the Poincaré B extension and try to prove a zero estimate. And it is because of this situation where we are not in a group variety, I cannot completely do the general case of a zero estimate, and I still have to do case by case analysis for the time. Okay, so I think I need to stop. Thank you very much.
Questions or comments?
Bien.
So when, in your result, in your theorem, you have this implication when the height is small, you get
Yeah.
Can you say more about the dependent information? You can bound, for instance, the distance between the or something.
The distance, you mean the anamorphisms that are going to, no, they are not going to be linked by, they are going to be linked by something that will depend on many things, and this will not be actually significant. Because in fact, even if you have a very high dependence relation, what happens is that there will exist a Riemann point, and that point will be infinitely divisible over the torsion field, which means that it will beat the lemma bound. So in fact, in any of these fibers, for any of these things, you will have at least one point which is for which the lower bound is not going to be.
More questions? Okay, in that case, let's thank the speakers.